Hey guys, I'm going to post, or you already see this because I've already had posted it. There's a post of the answers for the review packet, for the review questions of the textbook. Because I looked at the textbook, and some of them just says your answers may vary, and they don't give you any answers. So I realized how useless that is. So I just wanted to talk up through them and talk about my explanation. Now, usually in these videos, I do it live, but to cut out the wasted time of drawing stuff along the way, um, and respect your time because you guys are spending a lot of time studying for this. I'm just already have it completed. I'm just going to talk a little bit about like what's happening along the way. So I'm just going to go through it. Number 9, here we have 1 minus sine squared x over here. I think you guys could see my pen. If not, this is awkward. I'll just use purple. But you have 1 over sine squared x over here. So then I just made that cosine squared x, and then now tan is sine over cosine, canceled out. Now this is where it's difficult. So then I'm left with, after I do the canceling out of the cosines over here, I have sine and cosine. Now looking at this, I have a 2x inside the sine. So that's a big hint. I'm going to have to use the double rule. So in this one, I use the double rule to my advantage. And I know the double rule needs 2 sine cosine. So I'm going to put a 2 here, but I can't just add numbers for free. So I have to divide it by or multiply by a half outside. I cannot add numbers for free, but I need this to match my sine double rule. So I'm going to put the 2 here in green, but when I put that 2 here, I have to put the 1/2 on the outside. Once I do that, I can rewrite that as the double angle over here. So I'm 1/2 sine 2x, and that matches what I have. Number 10. This one is a lot more straightforward. You expect something like this. Tan squared plus 1, that's a trig or a Pythagorean one. So that's secant squared x cosine. I've made cosine into 1 over secant. If you made secant squared x into 1 over cosine squared x, that's the same thing. You'll just have to do a little bit extra steps to get back to secant x. But because I changed cosine to 1 over secant, I could cancel these out, and I'm just left with secant. This one, this is also a very common one. Be prepared for this. You have a cotangent in both of these, so you can factor that out. So I have a cotangent on the outside, secant squared x minus 1. That means it's cotangent x, I can rewrite that as tan squared x. Same concept as the previous one. I just made cotangent 1 over tan, and tan over here, reduce the tans. Cross those out. Again, if you turn this into a cosine sine and sine cosine, you'll still get the same answer. It'll take you a little bit extra steps, but it still works. So this one, you have sine cubed and you have a sine here. So take that out again. So you factor that out. Sine squared x, cosine squared x, that's straight up the rule over here, which is 1. So sine times 1 is sine. All right, so this one, I did it the long way. So I'm going to go to 14 first to talk about what is a better way to do this. So 14, I factor out the sine squared x, and I'll go back to 13, go sort it, or whatever the previous one. I factor out the sine squared x, and then had 1 minus sine squared x cosine x, which you could rewrite to cosine squared x. Cosine squared times cosine to the first power is cosine to the third power. So that worked out. Now here, I did it a really bad way. I could have taken out a cosine squared x first. And if I did that, I would have cosine squared x on the outside. And what I would be left with is 1 minus 2 cosine squared x, or I'm sorry, cosine. If I took out squared x, yeah, I'd be left with squared x plus cosine 4x. And then from there, I could do the trinomial, 1 minus cosine squared x, 1 minus cosine squared x. And that would have looked a lot more easier, and you would have skipped right to this step. But I didn't do that. So I saw this is going to be a 3. So this is a square trinomial. So I took it out and I made it cosine minus cosine cubed, cosine minus cosine cubed. If you don't trust it, you could FOIL it back out to get back to here. And then after that, I took out and factored out both cosines from here. So I had 1 cosine, 2 cosine, so that's cosine squared. And over here, 1 minus cosine squared is sine squared x because of the Pythagorean identity. So sine squared x, sine squared x, sine squared x, that's 5 sine x's. Okay, very interesting problem. Expect something like that. Definitely guaranteed it's going to be like something like these. These are guaranteed. This one I really like. I might put either this one or some variation of it on the test. Okay, so this one, it wasn't clear what they wanted you to do, and that's my fault. They're just showing you how this is how they wanted you to break this one up, because technically there's multiple ways to get to this point. So they're just showing you how to break this one up in this way. So they're basically forcing you to do it 2 pi over 3 minus pi over 4. There might be other ways to get to 5 pi over 12, but they're just showing you this is how I want it to be broken up. On the test, I will not tell you how I want you to break it up. That's your choice, which means you could choose to double it or cut it in half or add it or subtract it, whatever you want to do. So here we have sine 2 pi over 3 minus pi over 4. So sine 2 pi over 3. So I'm following the rule of the difference of a sine. So it's sine of the first value, cosine of the second value, minus sine of the second value, cosine of the first value. This, I think the normal way it's written is cosine 2 pi over 3, and it'll be sine pi over 4. That's the normal way based off the formula. But since this is multiplication, they're commutative, so you can put it whatever direction. I'm following more something where you learn next year about derivatives. U times v prime minus v times u prime. You'll see that in the future. So little hint. But either way, then I just do all my trig functions. I don't have to worry about negatives or positives because they give me the exact value, 2 pi over 3. So this is going to be in the second quadrant. So that's a positive sine. First quadrant, positive cosine. First quadrant, positive sine. Second quadrant of cosine, though, is a negative half. So then you're going to have your answer to result into this. And doing more of these, I kind of realized most of your results will look like some product, some addition or subtraction of root 6 minus root 2 and over 4. This will basically always happen, which is very interesting to me. So keep that in mind. If you do add and subtract, you basically should result in something like this. I can't say that's always true, but basically because the sum and differences has to be between like a 45 and a 30 or 60, that should technically always happen. So I think that's interesting. If you don't think that's interesting, then all right. So cosine 225 plus 60. So again, they're forcing you to use this combo. That's fine. So I use the cosine rule, cosine u, cosine v, minus sine u, sine v. The plus and the minus are inverted for cosine. Then found each value, negative root 2 over 2, 1 over 2, negative. This is in the 225 is in the third quadrant, so that's a negative sign. And then sine 60 is a positive one. Oh, and cosine is in the third quadrant, that's a negative cosine. So same thing, it ends up reducing to a root 2 over here and a root 6 over here, which causes it to be root 6 minus root 2 over 4. I can't guarantee that always happens, but very interesting. It happens enough that if you have something like that at the end, you probably did it right. Okay, this one, they're forcing you to use the half rule. They're forcing you to do the half rule here. Okay, so because they're forcing you to do the half rule, over 2 or over 4 maybe, we're going to use the half rule. So the half rule is 1 minus cosine of u over 2. Now you can find what the cosine of 3 pi over 4 is, which is at the second quadrant. So that's negative root 2 over 2. So that's going to be a plus. Here, I just change 1 into root 2 over 2 to make it one variable. And then here, I got 2 plus root 2 over 4, all square rooted. You could leave it like this. There's a little here, you could just you could simplify it technically a little bit more. And you could square root the bottom. So that's 2. And just leave a square root on the top. That's fine with me. That's the same thing. But that's the same thing. You don't have to really think about it too much. But you can stop at the top circled one in black. This one, I will give a problem like this, but my triangles will be Pythagorean triples, because when it's not a Pythagorean triple, it becomes this like ugly amalgamation of square roots and stuff. So I'll make sure my answer is a Pythagorean triple. This is the only reason why this question is awkward, because you just have to do a lot more fractional stuff than normal. But either way, it's UV. So they give you U, I think they give you like sine U equals 3/4. So I make my right triangle. Oh, and they say it's in the second quadrant. So I make a right triangle that would be in the second quadrant, which would be here. The theta would be at the bottom right. So my height would be 3, and my hypotenuse, which is 4 over here. Remember, this is second quadrant, so your x value is going to the left, so that's negative. So this is -7√7. And you could do that by the Pythagorean theorem. And for v, I think they gave us, ooh, wait a second. I'm going to pause the video. I got to check something. All right, good thing I'm recording this, but I'm going to fix this up right now. I made a mistake on this. This should be cosine. So that means that, oh wait, no, I did it right. My bad. So this is cosine, -5√13. This is what they give you. So your theta's here, or you could say v's here. So this is -5 adjacent. This is 13, the hypotenuse, and 12 would be your opposite. That's a Pythagorean triple. Or if you don't remember it's a Pythagorean triple, you could use the Pythagorean theorem. So then I just pointed out what tan of u should be, which is √3√7 over -7. And then I pointed out what tan v should be, which is 12 over -5. Again, you could just rewrite that as -12/5. That's the same thing. Either way, we keep going. We plug that all in. We have to do a little bit of math, a little fractional algebra. That's not algebra, that's arithmetic. But you want common denominators between here, so that's 35. Here, you're going to multiply. I just made 1 into 35/35. So then I could put it all in one fraction. Since everything's over 35, I could just cancel those out. So then I just have this. Technically, you want to square root, you want to use a conjugate on the bottom. Don't waste your time with that. Just circle it here. Again, this would only happen because they didn't give you a Pythagorean triple. On your test, I'll give you a Pythagorean triple. Okay, let's see the next one, sine 2v. It's the same triangle, so that's helpful. And I'll do that the same way. So you could you don't have to redo every triangle, make your test a little less timely. 28, super easy. It was just 2 sine v cosine v because of the double rule. So I just plug into sine v here would be opposite over hypotenuse, which is 12/13. Well, cosine v is -5/13. That's the one they even gave you. So then I just multiply that all the way through. This is the square of 13 squared. So the only prime numbers that go into 169 is 13. So I know I can't simplify that. For tan 40 is tan 2v, which is this rule right here. So I just plug in the v for tans. Luckily, they're all whole numbers, no square roots. So put it all in, multiply this out. So I got 24/5. Over here, I changed my 1 into 25/25 minus 144/25. Did a little bit of algebra. Then I flipped this. I keep change flip. So I did the reciprocal. So multiply by 25 on top, 119 on the bottom. Then just do a little bit of algebra. Not algebra, arithmetic, and that's done. 46. So we'll see this one. So this one was pretty interesting. Cotangent, I could rewrite as cosine sine, but doesn't really help me with cosecant. So I'll just rewrite it as cosecant over secant. So sine goes up, it becomes cosecant, and secant or cosine goes down, it becomes secant. When it looks like that, then it's cosine, cosecant, and a cosecant. I can factor it out. So I got cosecant x 1 minus 2 cosine x, because I just made secant x cosine x equals 0. So you can separate each one and set it equal to 0. And then the top, cosecant x equals 0. And I just want to show you a graph. But cosecant, you could think of it as 1 over sine x equals 0. But in this situation, there is no way I can make any value in the denominator to cause the whole thing to be 0. And we could also support it graphically, and I just want to show you that real quick. But over here, graphically, this is cosecant 0. You'll notice there is no x-intercepts. There's never a point when your y value will become 0. So because of that, we could kind of say that there is no solution for this part. So this does not exist. So this does not add to your solution. So you can't plug in anything here that causes it to be 0. But the second half, you could, because I solved it. So it's cosine equals 1/2. So I do the antiderivative. Remember, it's between 0 and 2 pi. So 0 and 2 pi, so it's pi over 3 and 5 pi over 3. And that's a 60-degree angle. So you want to see that in quadrant 1 and quadrant 4. Okay. And that's it. Yeah. All right. So hopefully this helped you out with this little video. Otherwise, good luck. Keep studying. Make sure you do your homework. If you don't do your homework, you're never going to finish this test on time. Have a wonderful day.